Hi, in this video I'm going to prove the sophomore's dream. This proof is going to be precise, but being precise may make it boring. Let's begin. We are going to prove this equality, which is called the sophomore's dream. There's another equality similar to this, which is also called the sophomore's dream, but I'm going to prove this one. We are going to use a theorem in measure theory. It can be derived from the Lebesgue's dominated convergence theorem, but we need this more weak form. Let A and B be a non-degenerate interval in R. By non-degenerate, I mean A is less than B, so this interval has infinitely many points. And Fn be a sequence of continuous functions, all defined on A and B, to R. Let f be a function such that it is the pointwise limit of this sequence. That is, for every t in this interval, the limit of fn of t equals f of t as n tends to infinity. 3. Let g be a continuous function such that it dominates the sequence fn. That is, for every t in this interval and for every n, the absolute value of fn of t is less than or equal to g of t. G is continuous. In fact, it's not necessary to be continuous. It can be Lebesgue integrable instead, but we don't need that general form. You can assume that G is continuous. With these assumptions or premises, we have a conclusion. Then this Lebesgue integral exists, and the limit of the integrals of fn of this sequence, in fact, is this number, which is a real number. In fact, this limit can enter the integral and go here, and when it goes here, the limit of fn of t equals f of t. So this is, in fact, the integral of limit of fn of t, dt, as n tends to infinity. So this limit enters the integral by this theorem. We're not going to prove this, but this is a corollary of Lebesgue's dominated convergence theorem. You can search this name and find a proof for this, and then you can derive this corollary. I'm not going to prove it here. And this theorem is a theorem in measure theory. We have another known theorem. A known theorem is a theorem that I'm not going to prove. For any positive integer, k, we have positive integer or natural number. I may use the phrase natural number instead. For any natural number k, we have the integral of x to the k times e to the minus x dx from 0 to infinity equals k factorial. In fact, this is the value of gamma function at k plus 1. You can search gamma function. I searched it, and this is the definition of gamma function, which is the same as this, except that here is z minus 1 instead of k, and it is said that gamma of n equals n minus 1 factorial. So gamma of k plus 1 equals k factorial. Next, we have a lemma. For a positive integer k, a natural number k, we have integral of t ln of t to the k from 0 to 1 equals this, k factorial over minus 1 to the k times k plus 1 to the k plus 1. We're going to prove. You may say that ln of t is not defined at 0. In fact, in this video, there are many functions that are not defined at 0, but we will define them at 0 by limit. For example, the value of this at 0 is the limit t tends to 0 plus t ln of t. So it is defined at 0, but its definition is this. Also, in the sophomore's dream, we have something like this. X to the x is not defined at 0, but we define it as the limit of x to the x as x tends to 0 plus, which is 1. So it is defined at 0 now. Now let's continue. For t greater than 0, we have the indefinite integral of this equals this. In fact, we could add plus c, but we don't need it. I mean that this is an antiderivative of this. This is that equality, and I'm going to prove it. I'm not trying to integrate. I'm just going to prove this identity. All I need is to differentiate the right side of this equality. Let's write this constant, 1 over minus 1 to the k plus 1 to the power of k plus 1. And now to differentiate this part, I have to differentiate this lower limit first. Let's differentiate minus k plus 1, and the derivative of ln of t is 1 over t. Then we must substitute this part in x in the integrand of the integral. X to the k becomes minus k plus 1 ln of t to the k, and then e minus k plus 1 ln of t. And because this is the lower limit, we need a minus here. In fact, if we have an integral like this, f of t, g of x, dx, and we're going to differentiate it with respect to t, it becomes d over dt equals f prime of t with a minus because it's a lower limit. The upper limit can be anything. And then we write g of f of t. This is what we did here. This minus 1 is needed when the function is in the lower limit of the integral. Now let's simplify. This minus and this minus cancel each other. Let's simplify this. Minus 1 to the k plus 1 to the k, and ln of t to the k. But we have a k plus 1 here, and we can remove this and add plus 1 here. And now this and this cancel each other, so we don't need them at all. What is left is this. And let's simplify this too. Minus and minus cancel each other, so we don't need them at all. K plus 1 goes here as a power. It becomes ln of t to the k plus 1, and so it becomes e to the power of ln of t to the k plus 1. And e and ln are the inverse of each other, so it becomes t to the k plus 1. Let's rewrite all of this. 1 over t times ln to the k of t times t to the k plus 1. And this t and this 1 cancel each other, and what remains is t to the k and ln to the k of t, which can be rewritten as t ln of t all to the k. This is the integrand of this integral. So derivative of this is this, which is this. And so the identity is proved. Now, note that here we assume that t is greater than 0, because at 0 this ln of t is undefined. For t greater than 0, we have this identity. So for any a greater than 0, we have the integral of this from a to 1. We add lower and upper limits to this integral. We get this. We give 1 to this function, which we can call it h of t. To calculate this, we should find h of 1 minus h of a. But what is h of 1? We have to calculate this. This is constant, so we write it here. To calculate h of 1, we set t equal to 1, and this becomes 0, so what remains is this constant times this. And to calculate h of a, we write this constant first, and then we write this with t replaced by a. So we get this. Now, this integral minus this integral becomes this integral. Their integrands are the same. The first one is from 0 to infinity, and the second one is from minus k plus 1 ln of a to infinity. So this minus this becomes the same integral from 0 to minus k plus 1 ln of a, and the integrand doesn't change. So we get this. So the integral of this from 0 to 1 becomes this integral as a tends to 0 plus. But why? Because this is a continuous function. Note that we have defined it at 0 to be the limit of this. So it is continuous on the interval 0, 1. And if we denote it by f of t, because f of t is continuous on this interval, the function g of a equal integral from a to 1 of f of t dt is continuous on this interval. And because it's continuous, the limit of g of a as a tends to 0 plus equals g of 0, which is the integral from 0 to 1 of f of t dt. And that's why we can write this equals this, as a tends to 0 plus. But as a tends to 0 plus, this tends to minus infinity. And because k plus 1 is positive, all of this tends to plus infinity. So we get this. This constant doesn't change, and this integral becomes this, from 0 to infinity with the same integrand. But the previous known theorem said that this is k factorial. Let's check. Known theorem. For any positive integer k, we have the integral from 0 to infinity of x to the k e to the minus x dx equals k factorial. And we use this known theorem here, and so this equals this, k factorial over minus 1 to the k plus 1 to the k plus 1. And the theorem is proved. Assume that the integrals are Lebesgue integrals, but because these functions are continuous, you can assume that they are Riemann integrals or any other well-defined integral. The next theorem is what this video is made to prove it. The summation n from 1 to infinity of 1 over n to the n equals the integral from 0 to 1 of 1 over t to the t dt, or x to the x dx. Choosing another dummy variable doesn't change anything. Note that this is also a continuous function, and we define this at 0 by limit of t to the t as t goes to 0 plus. So it is defined at 0. In fact, by this, we mean the function f of t equal to 1 over t to the t when t is in this interval and 1 when t equals 0. So we assume that this function is continuous on the closed interval 0 to 1. Proof for any real number x, we have, this is the Maclaurin series of the exponential function, sigma n from 0 to infinity of x to the n over n factorial. So for any real number t greater than 0, we have 1 over t to the t equals e to the power of minus t ln of t. Why? Because 1 over t to the t equals t to the minus t equals e to the ln of t to the minus t, because the exponential function and the ln function are the inverse of each other, and this equals minus t ln of t. This is the same as this, so we prove this equality. And by this equality, if we replace x with minus t ln of t, we get this. Sigma k from 0 to infinity of minus t ln of t to the k over k. Integrating both sides, we get this. Integral of this from 0 to 1 equals integral of this from 0 to 1. But what is a series? It's the limit of a summation. The limit of this summation when n tends to infinity. I intend to interchange this limit and this integral. But to do this, we need the known theorem we introduced before. I mean this theorem, this known theorem. A and b is a non-degenerate closed interval. Fn is a sequence of continuous functions which converges to the function f. G dominates the fn functions, and the conclusion is that this integral exists, and the limit of this sequence is this, which is integral from a to b limit of n to the infinity of fn of t dt. So with this theorem, we can interchange limit and integral. Limit comes out and goes in front of the integral like this. But these assumptions must be satisfied. Here we want to do the same. This limit must come out and be placed in front of the integral. To do this, we define the same functions as the known theorem. The sequence fn is defined with this. Fn of t is this, fn of t. And f of t is the limit of these fn's as n goes to infinity. So f of t is this, f of t. Note that here we define fn at 0, but ln of 0 is not defined. In fact, the real definition is this. If t is in this interval and if t equals 0, then we define the function fn to be the limit of this sigma k from 0 to n minus t ln of t, all of it to the power of k over k factorial as t goes to 0. So for 0 we define with the same formula but as a limit. So fn of t is defined on all of this interval. The same is true for f of t. In fact, this is not the definition of f of t. The real definition is this, limit of fn of t as t tends to infinity, because this formula was not defined at 0. And g of t, to be the same as the g in that known theorem, is defined as a constant function. G of t is sigma k from 0 to infinity of m to the k over k factorial, which equals e to the m. What is m? M is defined to be the maximum of this function when t changes in this interval. Note that this is not defined at 0, but we define it to be the limit of this at 0. So at 0, this formula is 0 when t equals 0, because we want it to be a continuous function on this interval. Note that limit of t ln of t as t tends to 0 from above equals 0. So we can define this function to be 0 at 0. And with this definition, this function becomes continuous on this interval. So m is well defined and is the maximum of the absolute value of this function when t changes in this closed interval. Note that with this definition, the absolute value of fn of t for any t and any n is less than sigma k from 0 to n of the absolute value of minus t ln of t to the k over k factorial, and this is less than sigma k from 0 to n of m to the k over k factorial, because m is the maximum of this function on the interval 0 to 1. So on this interval, this summation is always less than or equal to this summation, and here we can write n or we can write infinity, k from 0 to infinity, but this is g of t. So the absolute value of fn of t is less than or equal to g of t, where g of t is a constant function, and so it is a continuous function on the closed interval 0 to 1. So all the assumptions of that known theorem are satisfied. And now, by that theorem, the limit of this sequence is this. And if we replace the definition of fn, we get this. And if we replace the definition of f of t, we get this. So this equals this. But this finite summation can come out and go here like this, and we get this. The limit of this summation as n tends to infinity is this series, k from 0 to infinity of this. So this infinite series equals this, which is the same as this. But we prove that for t greater than 0, this is 1 over t to the t. But because a single point is not important as an integrand, we can replace this with this inside this integral, and we prove that this equals this. So this integral equals this series, and now we can simplify this formula. Minus 1 to the k comes here, and over k factorial comes here. And this remains as the integrand of this integral. But in a previous lemma, we proved that this integral equals this. And now if we simplify, this cancels this, and this cancels this, and this remains. Now if I change the variable and let k plus 1 be n, then I get this series, n from 1 to infinity of 1 over n to the n. Here k plus 1 changes from 1 to infinity, and here n changes from 1 to infinity. So the theorem is proved. This integral equals this series.